Good morning, everybody. I'm Daniel Komaromy. I'm head of research at Tusk Security Labs. And as Eugene already alluded to it, I'll once again be talking about the topic that I've been working on for the most part of the past going on 13 years now, which is vulnerability research in basebands. So on this topic, there's both a lot of prior art and very little. I'm just going to say that once, but when I say prior art, I mean public. As with lots of things in vulnerability research, this area also, of course, has a lot of stuff under the tip of the iceberg. But if we go by what's been done publicly, then starting from when it was super niche with Ralph's original seminal talk, All Your Basebands Belong to Us, 13 years ago, by now we have had lots and lots and lots of publications on remote exploitation of basebands. But on the flip side, despite the fact that in modern system-on-chip systems, the basebands are inherently an isolated context, and getting code execution in the baseband doesn't give you control, obviously, or automatically over the things that somebody wanting to exploit a phone would probably be after. Which should motivate that the existence of research publicly as well into what some people like to call sandbox escapes, others like to call pivots. The fact that there's not an established term in the public discussion, I think, shows itself very well that this is the stuff that isn't talked about. To the point where, apart from like a sensationalist backdoor story from about 10 years ago, which, once again, if anybody remembers or not, is just a normal, regular vulnerability, but was kind of hyped up as something else. Apart from that, and apart from the work from my team over the years, there really has not been any work on this part. The closest that we can find is the really great research from Gal from a few years ago about hacking Broadcom Wi-Fi chips remotely. Which is obviously adjacent and a similar situation, but clearly not a baseband context. And so basically, my goal was to try and once again do something in the public domain that could be novel, new in terms of the architecture that's looked at, in terms of the attack surface to find a bug in terms of the way the bugs are exploited, and most importantly, in terms of actually, once again, producing complete chains of vulnerabilities to go from zero-click to the baseband to the application processor. And to target new architectures, our original goal was to look at the newest iterations of the Exynos chips that Samsung has, as well as Mediatek's new at the time Dimensity chipset family. And so those are the goals. And then, like so often in life, you have a goal, and then the goal is maybe aspirational, but you might not necessarily reach it. As I go through the story, you'll see what I mean. So first we're going to talk about Samsung, and then we're going to talk about Mediatek. So it's been oft-repeated since our original talk with Nico Golde and myself, the first time the Samsung baseband was exploited publicly. The code name of the real-time operating system that Exynos basebands run is Shannon, so that's how in the literature it's usually referred to. And nowadays we're talking about a Cortex-A ARM chip that runs this. So it's not, so it's an inherently fairly accessible thing, not some kind of arcane ISA or unheard of setup. And in fact, when in 2023 you go about reverse engineering this target, two things become apparent very quickly. One is that, of course, lots of prior art has now been done, so there's many things to go by. And secondly, conveniently for somebody like me, not a whole hell of a lot has changed in terms of the firmware and the reverse engineering since the Breaking Bad talk. So the firmware formats that Samsung uses is still the same. The internals of the real-time operating system in terms of the lower layer level of the microkernel and its hardware abstraction layer implementations is still the same. The RAM dump-based debugging possibilities that existed already then has still not been removed or altered in any way. And even better news is that the amount of public tooling has not gone through unlucky bit rot, but instead the exact opposite. For example, the old IDA tools that I published back in 2016 have been updated and refreshed thanks to the Grant Hernandez to basically offer the same support on Gidra, which is good for everybody who minds their reverse engineering tool budget these days. And also, very importantly, over the years, a lot of different options for emulating these baseband firmwares have emerged. They all have limitations and drawbacks, but it's unarguable that it's a much friendlier target now to get to working with, to the point where I would really call a Samsung Shannon baseband basically a commodity target now. And if we go from reverse engineering to exploitation, which is the other part, then definitely on this there has been changes though. So Samsung has certainly made progress. They switched from the MPU-based Cortex-R system to, like it says, a Cortex-A now, which means an MMU. They fixed their long-standing problems with the NX configurations being totally out of whack and becoming meaningful. And of course, they have covered now their bases with like the most simple, buckless eradicating mitigations like random value stack cookies. However, on the other end, when we started, there was still no publication at all on heap exploitation in Samsung. So that was something that I was motivated by. And then I failed immediately in my plans of publishing on that as a novelty, because what happened is this is something the work was carried out in March of this year. So about a month of work is what I'm talking about here in our team. And in that time, we dusted off our reverse engineering tools, made sure that they are ported to the new chipset, came up with an idea of an attack surface to look at, managed to find a chain of vulnerabilities in it, which allowed us to put together actual remote code execution. We're able to use some exploit approaches that haven't been done before, at least not in a public setting, and then reported all of that to Samsung, including the total exploit POC. And then we started waiting, and then while we were waiting, and this year not one but two Exynos baseband talks have of course been done, a great one at Offensive Con and another one at Black Hat, both of them of course being heap overflow exploits, both of them of course overlapping with the techniques that we used. But the kicker is that the embargo, unfortunately, is still ongoing on this vulnerability chain. So not only is it not necessarily novel in some of its parts anymore, it's also not something I'm able to talk about here. So that's a fail. But luckily, there are other bugs. So even though this was sort of a last-minute thing that I had to adjust to, I pulled another recently fixed bug out of the proverbial hat, so that we have something to talk about. But this one really, admittedly, doesn't really fit at all the criteria of being a novel attack surface. It's another bug in layer 3 NAS message processing, in this case, in the session management of LTE. It was released actually in the June security bulletin. So this is a vulnerability that I had knowledge about, but I'm not the one who reported it. Nonetheless, following the bulletins, I was able to figure out that that's what this bug is. As you can tell from the previous slide, where it's worth going back to, if you read this very rich context, right, it tells you exactly nothing about the bug at all, which is random luck of the draw. Samsung bulletins Some of the entries are actually very descriptive and tell you almost down to the name of the function of what the vulnerability is, and some of them are like this, like we fixed the bug. Thanks for coming to my TED Talk. Luckily, however, Samsung, at least when it comes to their basebands, does have a propensity of creating bug fixes for reported vulnerabilities that are pretty noisy. The green is basically the diff of the fix, and the thing you want to see there is, apart from a check on a value, which I'm going to explain in a second what the nature of the vulnerability is, the thing you want to see is the new log message with a very helpful ASCII string. And in practice, those things make patch diffing much quicker and fairly conclusive, and give you a very good idea of where the bug might be at. Those are the guys who were present at the training that we did this week. You actually went through, obviously, the exercise of patch diffing this out. So, long story short, this is a vulnerability in an information element that actually hasn't been one of the ones in NAS that has been identified for vulnerabilities so far. But it's very similar to the other usual suspects, like your emergency number lists and AP element lists. It's another information element like that. It's called the traffic flow template. And it's part of the messages that are used in session management to set up a context. The way you want to think about the context, a PDB context or a PDN context, different names are used in the different radio access technologies, whether 2G, 3G, 4G, so on. What you want to associate this with in your head so that you can put it somewhere is, this is the I have internet session. So when your phone goes from it doesn't have IP to it has actually acquired an IP from a cellular network, that's what a bearer context means. And basically a traffic flow template is the idea of setting up or allowing the network to set packet filter rules. So specifically, these are broken down from one template to a number of allowed packet filters for every context, and within a packet filters a number of components. And then these components, every component is going to define some combination of a source and destination port or IP, and that basically can then be used to set a filtering rule. Where the vulnerability lied, and this is not an outlier in baseband vulnerabilities, is that the specification actually didn't really give the implementers such an easy time, because nowhere does the specification say what is the maximum number of components you should allow. What there are is these sort of free-form descriptions of various mutually exclusive rules of, you can have this type of IP address, but if you have a rule for this type of IP address, like IPv4, then you cannot have another IPv4 rule, but you can have one IPv6, but then, and then it's rules like that, and it's a little bit like a middle school math problem where you're given all those requirements, and then you ask like, okay, so what does that mean? And so exactly, you can read this carefully and sort of come to the conclusion very easily and straightforwardly what is the maximum number of components implicitly that are set. But unfortunately, in Samsung's case, in the Shannon code, they did neither of the things that would make the parsing proper. So neither does the code follow these mutual exclusive rules at all, nor do they have at least, or had at least, an explicit counter to say, okay, you cannot have more than X number of components. And what that meant is that the only thing that limited the number of components that the Shannon code would be willing to parse out is just a simple equation at the bottom of the slide. And unfortunately, in Samsung case, the static number of the array size that they always allocate to put the components happen to be a smaller number than what the division allows. And that's it. That's the heap overflow bug. So when you're talking about a vulnerability like this, then obviously there's really three important things. One is how are you going to be able to debug this at least in some way? I think anybody who has ever attempted to exploit a heap corruption type vulnerability will attest to the fact that doing that super blindly is not a fun time. I wouldn't say impossible, but definitely not something that, I would want to do or you should attempt. And then besides giving you some kind of debugging capability, then the second thing that you typically need to be able to do is come up with a way to control the heap layout, because things will not automatically fall in a way that what you will overflow out of will be adjacent to exactly a perfect victim for you that you are overflowing in, and so on. In this project's case, both of those things were, luckily for me, simple, keep it simple, stupid answers. In terms of the heap debugging, I literally had to do nothing new at all whatsoever, because the things that already were true 8 years ago, that from the telephone HMI menu, the human machine interface menu, the thing with the stars and the pounds, you can straight up set the phone into a debug mode, where if it operates in that mode, then it does two things on the baseband. One, it continuously collects a trace of the events that happen on the heap in a really large ring buffer. And then the second thing it does is on demand, it generates a full true RAM dump of the running baseband system, including this ring buffer with the events, which means that you can basically perfectly reconstruct not just the final state of the heap at the time when you got the RAM dump, but even how you got there. So that's sort of like a heap exploit developer's, wet dream. I guess a real, true breakpoint would also be nice, but you can definitely work with this. And then in terms of heap shaping, I find this to be the bane of my existence every time. It's like, okay, this heap bug, okay, well, how do we get shaping primitives from? And I've been asking this question to anybody else that I've ever talked to, of like, okay, in the whatever code base, all right, how do you find a spray primitive? How do you find? I think that's one of the hard problems, but like this case shows, sometimes you just get super lucky, either because some primitives have already been documented and they remain valid and you can just reuse it. But this is unfortunately more true for cases like Linux kernel or whatever, where there's a lot of rich work there. In this case, there was none. However, we got lucky because, as if we were in like a capture the flag competition, the bug just happens to also be a super perfect heap shaping primitive. Because as the slide explains, the network gets a lot of control over not just one time allocating any number of packet filters, but on the fly deciding to add more or delete any of them. And the total number that we can have goes up really large because, although this might not be apparent to you, your phone is capable of having as many as 9 different contexts concurrently with the network. That means 9 separate IP addresses. This is something phones actually use, for instance, when they do voice over LTE. Typically, that means at least another second context gets created, and then the IMS communication goes over that one, but normal networking goes over a different one. I mean, you can see where this is going with the bearers. It's all about the opposite of net neutrality, right? And allowing the carrier to have different QoS provisioning for different bearers, which is obviously is fine and compliant with everything. But for us, it's good that they wanted to do this because, the things multiply up and we have an abundance of ability to allocate and delete and basically create checkered patterns. So at that point, the last thing or quote only thing we need is a good thing to overwrite. And here, this could have been super quick because like I mentioned, the technique, this technique has now, been publicized and made famous in a couple of talks this year. It doesn't really deserve too much explanation. It's just the classic unsafe unlinking, problem, very typical with heap allocators that also, reared its ugly head here. However, in our case with this bug primitive, unfortunately, it's useless. The reason is that if you were paying attention, you notice that the problem with the vulnerability here is that we get an overflow if we get too many components. But to this moment, to not confuse you, I haven't explained to you where the overflow is. And the overflow is not in a concatenation of components because they are kept separately. The overflow happens in the array that maintains pointers a list of pointers to the existing components. And what that means is that our overflow primitive is not values that we control. Our overflow primitive is pointers to values that we control. And in this case, for this particular primitive, you need the very simple thing of one of the least significant bytes of a heap header would need to be overwritten with the value 1. But since we are only writing pointers and those are always 4 byte a line, it's just not going to be possible to ever write the value 1. So you cannot trigger that technique. And so instead, there's a number of different things that obviously you can try with a pointer override type primitive like this. And I had some limited success in terms of finding primitives that or finding victims that fall into one of these categories. But unfortunately, it too significantly overlaps with the actual completed exploit for the other thing that I'm not going to talk about. And I don't want to play games with like, okay, just a tip, we'll just talk about it a little bit. So we unfortunately have to leave it at that and work in progress. Plus also in the interest of time, we want to continue anyway. So let's look at the other side with Samsung. So since we had a split we wanted to look at both Samsung and Mediatek within that period of time, we made the decision to try one attack surface for one and then other attack surface for the other. And specifically for Samsung, we decided to try and look for bugs in the user space, and for Mediatek in the kernel. So first I'm going to talk about Samsung. And so when I say user space, what you typically going to mean is what is pretty much the most obvious and also at the same time the largest attack surface if you're thinking about going from the cellular processor / baseband / modem, whatever you want to call it, to the application processor, which is the implementation of the radio interface's IPC mechanisms. So actually this is an interface that actually many years ago there was a time period when it was receiving constant significant attention, but in the other direction. So in the direction of can you find corruptions and vulnerabilities on these interfaces in these phones, but from the application processor to the cellular processor. It might not be apparent, not thinking with 10 years ago brain why that was the case, that the hacking community really cared about this, but the answer is in carrier unlocking. So if you think back in the day, go back 10 years ago, you had things like, yes, you could buy an iPhone in the United States, but only on one carrier. And so there was for a while a very active community, actually in people overlapping with the iPhone jailbreaker community that continuously tried to basically hack basebands from the application processor side with the target of defeating the carrier lock limitations. But then this was something that sort of went away because, it became a solved problem, essentially. Nonetheless, the IPC mechanisms remained, and obviously it was a quite reasonable thing to ask that, if vendors have a track record of messing up the parsing of these implementations on the one side, perhaps maybe the other side was also not completely rock solid. And then in terms of what the commands are supposed to be, it's a good fan out because while on paper there's an old standardization for this, the AT commands or Haynes commands, in practice for a long while now, most of the phone vendors just use some completely proprietary implementation they have. It's QMI as it's well known for Qualcomm, and the list goes on. In the case of Samsung, I could say it's called SIPC, but when I say it's called something, I just mean like whatever strings seem to refer to in code. But the point is that this is something implemented in the user space, specifically in the radio interface layer daemon. And now at this time, the talk could sort of take a detour into, this used to be a baseband talk, but now it's basically Android user space, C++ code reversing / exploitation talk. Really honestly, for me, all I'm going to say about that is like, oh, this is amazing. This user space stuff is fantastic. Everything is an ELF, so you don't have to worry about like what the firmware format is. You know, you can root the environment you're working in. There's like out of the box, super well working debugger and tracer in the shape of things like Frida. And also when you start looking at the SO that you loaded into your IDE or whatever it is, you know, you're not starting out with like, here's 110,000 totally unlabeled functions. I wonder what is what because I know nothing, but you're starting out with every function has a name, you know, lots of the objects have like the type definitions, and there's a couple hundred functions that I sort of need to look around to figure out where are the handlers that I'm interested in. And so really when things are this descriptive in their name, it's sort of easier to jump into. But of course, you could say the same thing about Chrome, and I would argue that it's not trivial to find bugs in Chrome. So just because obviously something is an ELF and whatever, even when it's open source, I mean, the code quality and maturity and complexity can, you know, flip this whole thing on its head. But that only applies when there aren't insanely trivial bugs, which wasn't exactly the case here. So I really don't think I need to dwell on these. It's like, I mean, these are a couple examples, but it's almost, I mean, like it's literally what it says on the label. So a type of message where the IPC comment on the surface, most surface layer includes, this is the length of the message I'm sending, and this is the message, and then that's a straight up stack buffer overflow. Or here's another one where it's the same thing, and this is straight up heap or buffer overflow. So this is literally like tweetable POCs level. So in terms of all bugs, it was actually quite fruitful quite quickly. And in terms of doing something with it, being able to test and everything, obviously, since we have root and everything, we can easily test our hypothesis without a fully working baseband remote exploit as well. And so there's like cool and everything, but obviously, you know, if you're even remotely familiar with Android user space realities in 2023, you know, just because something is like, oh, a stack buffer overflow or a standalone heap overflow to a certain fixed size buffer, you're very far away from like exploiting this, never mind reliably, but even in some like super crappy, at least it worked for the conference type of way. Just because of the realities of the very strong mitigations that you expect there to exist. Obviously, remote exploitation, when you don't have some kind of scripting engine type of setup, usually is immediately difficult, but that was already true years ago. But now, you know, the Scudo allocator that Android user space has is, you know, much more aggressively designed to thwart different types of object memory safety bugs. And the list goes on. So at the first order, you could say that, so it's a remote bug and we don't have a JavaScript engine. Okay, good luck with that. Why don't somebody else work on this project? I'm moving on to new bugs. But at the same time, maybe, if you have, you know, a really powerful enough set of bugs, then you can be lucky. The long story short here is that while some things came out in July, that only represents a subset of the things that we identified. And so completing this would once again require some others. So to be continued another time. So now you guys understand you can understand what I meant when I said that best laid plans sometimes don't work out, even when quite a significant time ago you have spent the fully working exploit POC to the vendor. You might find yourself on a stage basically just saying, I do have an exploit, you're just not going to see it. So this is I totally have a girlfriend, she just lives in a different city exploit this time. And so let's move on to Mediatek. And in this case, the things the whole situation was almost the mirror image of Samsung. When it comes to firmware reverse engineering, it was much more of an original work or a challenge, because when MediaTek moved up a chipset family and went from what they codenamed Helio to Dimensity, they kept the same real-time operating system, but they replaced the ISA. So they moved to nanoMIPS. And nanoMIPS is one of those instruction sets that is just not supported at all by the common tools of the trade. So your GIDRAs, your QEMUs, your IDAs, your existing GDB tool chains, and the list goes on. It's just not there. In our 2020 blog post, when we did baseband exploitation on Helio MediaTek basebands, we explained in detail how you can write fairly not painfully, I would say, a decompiler plugin from scratch for GIDRA. So if you're interested in those aspects, then I would encourage you to check out our blog post from last year. What I'm going to say is we basically followed that roadmap to also get support for nanoMIPS. And then in terms of things like emulation, thank you so much to Ivan, who very timely at the beginning of this year, I think in March or April, released upstreamed his patches for exactly QEMU, or at least one of the forks of QEMU for Hexagon. Because one of the things, if you've ever worked with QEMU, it's one of those programs where it's actually it's structured and built and implemented in a way that really makes sense. It's just a lot of that is not documented. So if you want to extend it, then you somehow have to like get the magic incantation of like knowing how you're supposed to be doing things. But obviously when there was a set of patches of this is exactly how you add the new language to it, that was kind of straightforward to follow, to replicate for a different language. So thanks. Here's some screenshots of our emulator in action and GIDRA with nanoMIPS decompiled code. And then came a part of like, let's find bugs. And here, where I started, it's worth throwing up again this slide and see lots of people did lots of things. So maybe it would not so be easy to like find something that you can say is like novel or whatever. But one area that wasn't really explored all that much is actually layer 2. So with all of that background, if we then say, okay, but where are the ones that are not layer 3 and above? Then the list very quickly, unfortunately or fortunately, went down to 0 publications ever. And probably it's because people often listen to smart people. So this is a quote from Ralph's original Usenix paper. This is the Usenix wood paper version of the all your basebands belong to us talk, in which one of the points he made is that in terms of attack surfaces, layer 3 is what usually makes a lot more sense for like larger attack surface. If anything, there could be bugs in layer 2, but more one-off or whatever, because the message sizes are very small, so there's not a whole lot that can go wrong there. And so at this time, I figured like, okay, well, let's see. Obviously, spoiler alert, obviously there's a bug on the next slide, but I'm not actually in any way advocating that this sentiment would be wrong. If anything, my experience with it really actually reinforces this. Like, it's not an area where it's like bugs everywhere like it used to be with TLV parsing in NAS. But if you know where to look, there's still one of things that can go wrong. It needs a little bit more specification reading and thinking about it. Yeah. So in our case, what we identified is a bug in the GPRS layer 2, which would be radio link control. Here's the timeline of when we did the work. And the important part is, like, in this case, everything that we found were fixed, and the timelines worked out, and we had no issues with being able to talk about all of them at the conference. So now there can be some completed stuff, at least at the end of it. So this particular vulnerability like I said, it's almost everything is going to be the mirror image. So in this case, the vendor actually puts out a description of the bug, which is knowledgeable, and then you can read it, and it says which protocol and which message and what is the bug class or bug type with it. Excuse the joke or whatever, but it's a recurring thing that sometimes there's a description and it's great and everything. The only problem with it is there's nothing in it that's true. So in this case, this vulnerability is not in radio resource, so they didn't get that right. It's in radio link control, and when it says that the problem is that the neighboring cell size in this message is improper, there's no such thing as the size of a neighbor cell as field in this type of message. So when you understand the MediaTek implementation, it becomes intelligible why they wrote it like this. But the point is that sometimes, even when it seems like it's a description and it tells you that's where you should be looking for that type of bug, maybe it's not where you should be looking, and maybe it's not that type of bug. But the long story short is that this actually ends up being something that is very similar to the CSN1 type vulnerabilities that we have previously talked about in a couple of contexts in previous publications, in that the grammar definition for this type of message basically states that, okay, in these PNCDs, what you can have is a number of elements, which here they call containers. But the key is that we go back exactly to what we said here, is that these messages are too small. And this is something that happens a lot at layer 2, that they don't give up just because the message is too small, but the way they define the specification is like what it says there, which is probably too small to read, and I apologize, but it says container continue the next message. So because you cannot fit enough containers that would fit the purpose into one small message, the specification allows one message to say, oh, and there's going to be more containers in the next one. And so actually with one small trick, now again you can you don't have to worry about things like my message is too small. And we kind of find ourselves in a situation where, okay, what this means is there has to be some resegmentation implementation. So the radio link control layer 2 code in the MediaTek implementation somewhere needs to handle the fact that PNCD messages keep coming with new and new and new containers. And of course, the specification doesn't say anything at all about like what's the max number you should allow or whatever. You should just like, not have a heap buffer overflow. So in this case, that didn't work out. So as you could see on the code slide, so the implementation was just the most basic naive. If there's more containers, let's do it. And there was just no limit at all to how many containers it would be willing to assemble into its list of which then eventually overflows. So here, like I said, once again, everything is the mirror image. So whereas in the case of Samsung, you get like nice debugging capabilities for free. In the case of MediaTek, there's not really something like that. We did do some work on doing something not this super hacky level of, well, if you look at the kernel D message, you get some idea of like when things are crashing with memory corruption in the baseband. In our trainings, we talk about the details of how we do like baseband debugging for MediaTek, but here there's no time or space for that. But with something like this, you can already get along. And another thing that I'm not going to talk about because of the interest of time is, okay, again, another setup. You have a heap overflow. What can you do with it in this context? What I'm going to say is that the release that we did last year, where we talked in detail about what the nucleus implementation exactly is like, and we identified some metadata-specific attacks against it. So when we looked at this at 2023, which is 6 months after MediaTek already fixed the bug, and 8 months after we have put out that blog post on the previous bugs. So MediaTek actually went ahead and really, I like this, kudos to them. This was never reported to them. It was just a blog post, but they very clearly read it and specifically modified the heap metadata implementation to kill those attacks, which I think is really cool. But nonetheless, so this year, again, half year after that bug was already dead, we did look at what you could do and identified some techniques that you could use. And in an upcoming blog post, we'll detail them a little bit. And then finally, the last piece then is also looking at going from the cellular processor to the AP. And in this case, we wanted to look at the one and done. So see if we can go directly to the kernel. That's obviously, if you manage to do that, then you don't need to keep thinking about even privilege escalation chains going on from, like if you're starting out with an exploit into the user space. And then the Linux kernel attack surface is, again, basically the total opposite of what you can find if you look for the real. It's going to be much smaller, much more specific of what can go wrong. But the few things that can go wrong, if they program exactly those things wrong, then you're very likely to end up with like really powerful exploit primitives. And the underlying reason for this is simply that IPC message needs to go through somehow. And the somehow in the case of system on chips is always shared memory. And then shared memory, communication over shared memory is typically, obviously implemented with your classic ring buffers that we all get as a coding exercise in school. And as everybody knows who has done that, if you think about valid behavior with ring buffers where you're sharing not just the area that you're continuously consuming, data from and putting data into, but you're also sharing, in this case, by design, the offset or slot ID or whatever the implementation is, values that obviously tell the other side where you are in the ring buffer. So really there's just one thing to get right, which is that whenever the other side tells you where the new slot or offset is in the ring buffer that you're supposed to be consuming something from, that you make sure that that offset you check and verify it's within the ring buffer. That's like the one requirement. And turns out even one requirement you can get wrong in 3 different ways. So in the case of one of the ring buffers, the fact that we can just set the length to whatever and the offset to whatever, in a straightforward way results in an integer wrap, making the only check useless and then turning into a stack buffer overflow, which is the type of vulnerability that at first sounds like, oh, on these specific devices, there's no stack cookie in these functions. There's no kernel ASLR. The values that I'm writing are controlled. So exploit demo for the conference, right? But actually in the case of this vulnerability, I was glancing over the small fact of there's an integer wrap which gets us around the length check. And this is obviously the typical situation that your length, the cost of you getting around the check is that your length that is then derived, flips around, so becomes a negative value. So if that's directly given into the mem copy, like in this case, then that's going to be a whole hell. So that's going to be a lot of bytes you're going to write. And, in a normal case, you immediately give up. Like, you're writing off the kernel stack because you're writing, 4 gig worth of bytes. Of course, this is going to be unexploitable forever and always. In this is a context where maybe you convince yourself to cause yourself a lot of pain by not giving up, because you can start convincing yourself that, well, it's a very special case because obviously we are one of the other cores in a system on chip. And one of the powers we have, because internally that's how we talk to each other, is we can fire very precise and non-preemptible FIQs, right? Interrupts, which is to say that we have this magic ability of telling with very, very strong precision, telling the kernel when to stop doing what it's doing and start doing something else. So you could say maybe it's exploitable, and kernel thread stack frames normally have guard pages around them. But yeah, maybe, kernels also are normally not without KSLR these days. So maybe we look for MediaTek device versions where they're not. But the long story short is, like I said on the slide, coparder. So yeah, okay. If somebody else wants to try exploiting this, then go for it. But I wanted a better bug instead, which luckily we found because right in the handling of the other ring buffer, it's essentially the same implementation or implementing the same thing, but in sort of the other way you could, which results in, again, the same idea. Because the offsets are completely controlled, you get to have a situation where, compared to the base of a fixed value, you can turn the writes and the reads into an arbitrary offset, regardless of where the ring buffer was supposed to be. And then there's limitations because the offsets are here on 32-bit, so that's the total you can write. And then here you would have to start thinking about, okay, but do I control when things get written and what gets written and so on? But luckily for us, one of the specific things that all this IPC is always for is supporting some notion of a virtualized file system. Because unlike Android, which always has access to the actual file system, the actual solid drive, the basebands typically don't have that access at all. They just have the memory access. And then they use the IPC to have the application processor virtualize for them the idea of basically what they usually call a remote file system. And what this means is that one of the things that these ring buffer based channels are used for is for the modem to say, write this to this file or read me back this file. And what this results in is you can actually control both the precise timing and the values of what gets echoed back. And so this very easily, without thinking, really gets around this issue, and we truly get we can write whatever you want, whenever we want. Here's an example of that. And now we're on the last slides, and basically there's only one problem left to do, which is obviously uinmax is the size of the offset. So actually on 32-bit kernels, this is clearly game over because that's the entire address space. So you don't even have to think about it. It's arbitrary read-write infinite number of times. So that's difficult not to win. And Helio kernels actually were still 32-bit. So a lot of the devices out today, continue to receive updates and everything, but they're not changing up from the 32-bit kernel that they originally had. But the Dimensity kernels are 64-bit. So at first it looks like, well, are we going to get lucky? But really, the long story short, and here shout out to Brandon Azad, who in a totally different context did some work on, okay, over heap corruption exploitation, but on VMalloc, not normal Kmalloc. And long story short here is that address space is really super packed. So even though at first the 32-bit sounds like maybe there's just going to be nothing there or not enough or the good things are too far away, in reality it's the total opposite. So within that 32-bit range, not always a constant offsets, but remember we can read as well, so we can scan. There's always really very rich targets because of the SecCom filters, tons of BPF programs, and all kinds of stacks for different threads, user-based threads and key-workers and things like this. So again, basically just sort of replicating the ideas that, for example, he talks about in his blog. You can win. There are actually some that are constant offsets even, because they are very, very early allocations. So you don't even need to scan. It will be like one shot, always from where I am, always at that offset. There's always this function pointer. So that's nice. And with this, we are at the end. We're 2 minutes over the 45. So I do apologize. Let's watch this little demo, and then we're going to do questions. So this is the pivot from the baseband to the kernel in question. Underneath it uses what I mentioned is our own baseband debugger implementation, which I don't talk about here, the details of it, but the point is that you're going to see that that's why we can run it from the host. So this is emulating, we just run whatever code we want within the baseband, and what just ran made the baseband do these ring buffer tricks. And as you will see, the end result, just to show that what we're doing is obviously we have modified the kernel memory in place. And with that, questions. We have minus 7 minutes for questions, I guess.
All right. Perfect. Thanks, Daniel. We have time for